Today we're going to be looking at water and the different properties that water exhibits, and it's connected to the intermolecular forces that we studied the other day. I want you to go through and draw the diagram for water. So again, water is H2O. So you're going to have two hydrogens bringing an electron each, and one oxygen bringing 6 electrons. Okay, altogether there's 8 electrons that we have to place into our diagram here. So again, let's lay them out. Here we go. We have hydrogen, oxygen, hydrogen, and so there we've used up 4 electrons. So now we have 4 more to place somewhere. So we're always going to try to put them on the peripheral atoms. So these are the hydrogens, but they already have enough. So the next step is to put them on the central atom. So 4 left. So we'll put them on like that. Okay, so when we change this to a Lewis structure, you'll have the bonding electrons change to a dash like that. So we have these 2 lone pairs, so that when we actually looked at the 3-dimensional diagram, so remember we had to look at, okay, so a structure that had, molecule that had a central atom, and then it had 2 peripheral atoms attached to it, and then 2 lone pairs. So there's 4 things attached to the center, right? So we're looking at, it's one of these here. So here, we're looking at this one here, right? So we have a bent molecule, okay, and then it's 2 lone pairs. So when you draw the peripheral atoms here, it's you need to draw the water like this, okay, so that it's bent. Okay, and then the lone pairs are there as well, like that, but they need space, so they bend away the peripheral atoms like that. Okay, so you won't have a straight line. All right, so so this is the structure of water. Okay, and so we know because you have a slightly positive and negative end. So this is the negative end, this is the positive end. Okay, so if we're looking at just the oxygen-hydrogen bond, like that, and then we're looking at the electronegativity values. So oxygen is 3.5, hydrogen's 2.1. Okay, so that gives you an electronegativity difference of 1.4. Okay, so remember when we were 1.7 and higher, we were considered to be an ionic bond. So we have a really high electronegativity difference. And so that's why, this one ends up with a slightly negative and that's a slightly positive. So this is, oxygen's really good at pulling those electrons towards itself, okay? So you get that slightly negative end. So that's why this is a polar molecule. So we learned the other day that, if we have another water molecule here, that what happens is that they will become attracted to each other, okay, because they are polar. So they have these positive and negative ends to them. So the positive end of the water will be attracted to the negative end of the water here with the oxygen and so forth. So you get the formation of the hydrogen bonds. Okay, so we're going to look at the melting and boiling points of water using these diagrams here. So we know that these hydrogen bonds require a lot more energy than other types of intermolecular forces. So we need a lot more energy in order to break them. Okay, so if you were just liquid water, okay, so if you were just the liquid water sitting in a beaker here, and your hydrogen bonded together, and then you add heat, you're going to find that they're going to start moving around faster and further apart, okay, and then turn into a gas and so forth. So with water, it requires a lot more energy to get it to boil than something similar to water, which is like hydrogen sulfide, okay, hydrogen selenide, and is it hydrogen, what is that, tellurium? So telluride, okay. So basically, if we're looking here at this periodic table, we have like we're looking and comparing if hydrogen, two hydrogens combine with oxygen, you make water. Two hydrogens combine to make hydrogen sulfide here, and so forth. So we're trying to compare with the ones down the family how the boiling point is affected here. So in general, you're finding that this is the blue one here is like kind of like a normal trend here. So if we're looking at the carbon here, carbon, silicon, so we're looking at this family here. So when they're combining with a couple hydrogens or four hydrogens here, you will find that in general, as you go down the group, right? If you go down the group, you're getting bigger and bigger atoms, right? Elements and so forth. So that means they're more massive. They have a higher mass. So when you add heat to these, it takes a little bit longer and longer for these bigger ones to start boiling because they are heavier. Okay, so that's like a normal trend. But what we're finding here is that there's these three that don't follow the trend. So in their families here, like if we're looking at oxygen here, oxygen is in a family with sulfur and selenium and tellurium and so forth. Oops. So you should see that gradual increase in the trend, right? But what we're finding is that oxygen, like whenever it's combined with the hydrogen here, you end up with a much higher boiling point. So it's not following the trend. Same with fluoride and ammonia here. Okay, so again, let's just go through and draw these structures. Okay, so I've drawn in a few of the group 14 structures here. So here's, methane. We have silicon, or tetrahydride, and so forth here. So again, group 14 is right here, this group here. So we're putting them and combining them with hydrogen here. And what are we noticing then when we draw these 3D structures? Is that, you can go through and look at the electronegativity, but these are all nonpolar. Okay, so they're nonpolar. So what you're finding is that the boiling points, they can boil a lot earlier, like at a lower temperature than the rest of these ones here. Okay, and again, if you're looking at it from an intermolecular force perspective, remember these ones, the only force that they're really going to have is the London dispersion force. Okay, you won't have the other forces on there. So that's why the boiling point is lower. Okay, and then in general, as you go up or down the group here, you get more and more massive atoms. So that's why it takes a bit more energy in order to get them to boil. Okay. Look at group 15 now. This is, I don't know, like we call these groups like group 14, the carbon group, the group 15, the nitrogen group. So looking at group 15 with nitrogen, phosphorus, arsenic, and antimony. So these ones here, if you draw the 3D structure, they form a trigonal pyramid shape in 3D. Okay, so again, if we want to look at the structures here, so we have one lone pair, okay, one lone pair, and then three things attached. So the trigonal pyramid shape. So the bottom is like a pyramid. Okay, like that. All right, so with these ones here, we definitely have a polar molecule. So these are polar. And so then you're going to have a slightly negative end and a slightly positive end. And you're going to find that there is definitely, there's going to be a London dispersion force. Okay, but there's definitely a dipole. Okay. And then if you do have, nitrogen, then you're going to have the H bonding as well. Okay, so you're going to have lots of different intermolecular forces getting them to attach to, so again, if you have another ammonia here, they're attached with these various forces here, intermolecular forces. Okay, so that's why when you go to boil it, it's a little higher than the group 14, right? Because they have these, at least dipole attaching them together. So you got to break the dipole bond in order to get to boil. So that's why they'll boil higher than the carbon group here. Okay, but then yes, nitrogen is a lot higher than these other ones because nitrogen, right, is part of that special FON. Remember the FON group, fluorine, oxygen, nitrogen. If you have that in your structure and you're bonding to another hydrogen, you're gonna um, have the hydrogen bonding effect as well. So that's why these ones take a lot. It's a way higher than the rest of the family here. Okay. All right. So that's the same trend that we're seeing with these other ones here. So we'll just do hydrogen fluoride group now. Okay. So here's group 16. So the halogen group here, and we're finding that these are all linear. Okay, so again, if we look here, just yeah, straight across like that. So linear, and but these do have yeah, poles. Okay, so there'll be a negative end and a positive end, and so forth. So these you will definitely see London dispersion force. But you can see the dipole, and then if you have the special fluorine, oxygen, and nitrogen, you'll see the hydrogen bonding as well. Okay, so that's why, again, these are higher up on the boiling point table here because, yeah, you have all these different forces that you have to break through. Okay, and then we'll go to oxygen. All right, and here is group 17. So, oh, this is group 16, sorry. So I'll change that. So this is group 16. And sorry, this was group 17. Okay, all right, so group 16 is, I just want to leave that for the end so we can analyze water here. So these ones here, these ones have a bent structure. Okay, so again, taking a look at the sheet here, whoops, one. So if you have, like there's this bent as well, where there's 3 of them, but we have there's 4 things attached. So when there's 2 lone pairs like that, you have a bent structure. Okay, so from here, you're again going to get the H bonding effect. You're going to get the dipole, the LDF. So you can have all the forces here helping it bond together. Okay, so again, that's why, again, they're higher than, so compared to this original, whoops, group 14 here, that's at the bottom here. So again, when they're nonpolar, you don't have these extra forces that you have to overcome in order to get to boil, where these other ones here, they have, dipole and H bonding as well. So you have to add more energy in order to get them to boil and break those bonds. So I know I went through here and I, put in H bonding here, but I meant that, H bonding only applies to, remember this one here, okay? These ones here have the LDF and the dipole, okay? This one here, the H bonding only applies to this one here, okay? But the other 2 have, so the water has all 3 of these, but on top of the H bonding, okay? And same with this one here, the H bonding, is happening here, but the other 4 here, the other ones in the group only have LDF and dipole. So the general trend here is that, as you get, you go more right across the table here, okay, you're getting more and more massive, so you're getting heavier, so it's going to take you more energy to boil. So you're seeing that it goes group 14, group 15, group 16, or well, it goes group 14, 15, then it goes 17, then it goes 16, okay? So there's a little abnormality here as well. But in general, you're supposed to kind of follow this gradual increase in boiling point, but these 3 here, because they have fluorine, oxygen, nitrogen, they don't follow what their group is doing. And then if you're just wondering why is 16 have a higher boiling point than 17 if we're looking at it from the mass perspective, it's because if you look at these structures here, see how this group here, they can form a lot more hydrogen bonds with their counterparts, okay? Where this one, when you're just linear like this, you can't form as many hydrogen bonds. So because there's a lot more hydrogen bonds to break through, that's why group 16 tops the chart here, okay, or tops the graph here and so forth, okay? Anyway, I'm showing you way more detail than you need to, but if you were just curious about just why the boiling point is different. What you should be taking from this is that the more intermolecular forces that you have involved in your in um, like between molecules. So if you have nonpolar molecules here, if you only have the one intermolecular force, you're going to have a lower boiling point. If you have more intermolecular forces like dipole-dipole as well, you're going to have a higher. So that's why these other groups are higher than group 14, because these are all nonpolar. These guys are all polar. And then if you also have H bonding, also affecting whether you cluster together and so forth, and that's what shoots up the boiling point as well. So these ones don't follow the trend of what's happening with the rest of the group. Okay, so it's all about the intermolecular forces. So another property that water has, it is high surface tension. Okay, so if you take a look here, I found a picture of where someone over poured a glass of water here, and then you see that kind of that extra, it's almost like a bubble at the top here. Okay, so that again is due to H bonding. And okay, so here I just poured a glass of water here, and I have it at the top here, so I think it's a little hard to see, so I'm going to pour some more water in. Okay, so you see it's right at the top, and it's hanging there, right? It's definitely past the top of the glass. Okay, so you can see it there. Water exhibits high surface tension, so you could think of it as like it's a property that it has the ability to withstand other forces like gravity, like the water should be spilling over here instead of just piling up on top here. So what's happening here is if we look at it, I guess just the molecules of water, they're H bonded together. Okay, and so you could think of it as like the water molecules are holding hands with each other, right? So if we quickly just draw a bunch together right now, so they're holding hands together with this H bonding effect, right? So here, just do a different color here. So when you have that, they're clinging together. So if you have this one water molecule, like this isn't, to scale at all, but so say there's one water molecule here hanging off the side here, okay? So why isn't it falling and dripping down and pouring out of the cup? Well, because there is another water molecule hanging out in here holding its hand, if you could think of it that way. So there's H bonding happening right there, okay? So, and then why aren't both of these falling off? It's because then there's another water molecule in here like this that is holding on to that water molecule like this with H bonding and so forth. So that's why water can exhibit this property here where, yeah, if you aren't paying attention, you over pour, you get that little kind of bubble at the top of water, and it's not going to pour over the side, and you can just sip it off and so forth. Okay, all right. Other things that you'll see though in a science lab is that sometimes I want you to go and measure the volume of something, and you'll use a graduated cylinder, and so when you pour it in here and say you needed 35 mils or whatever it is, you pour the water in, and then you have to go and take the measurement, and if you look carefully, you always see this kind of it's like a I don't know, it's like a little rainbow, upside down rainbow. Okay, so and then if you look here at this diagram, it's more clear here. So what you're going to be doing here when you see something like this on in the cylinder is that you have to read the bottom of that kind of that parabola shape. Okay, so they call this the meniscus. So when you need to measure something or read the measurement here, so you have 30, 35, so this would be 36 and a half, okay, milliliters of water. Okay, and so you're not reading the top here of the meniscus, you're reading the bottom, and that's how you read accurately. So if you want to look at this one here, it's 21, 22, so this is 21, 21 and a half, 21.5, 21.6. So this is 21.7 if you were actually measuring that out. So 21.7 milliliters of water. Okay, and the other one here is, this one was like 36 and a half. Looked like it was about halfway. So yeah, so anyway, this isn't about measuring today, but I just wanted to show you that when you are actually going through and pouring things into a slim container like this, like a test tube or a cylinder and so forth, you're going to find that there's going to be a meniscus forming here. So water is going to have be pulling up the sides and so forth. Okay, so it's the opposite of what's happening here. Okay, you're just making kind of a bubble at the top here, and the water's not falling because of H bonding. But the same thing is happening here with the glass. So this happens in glass of the cylinder here. So if we look at a bigger picture here of this here, so what's happening here is that these are the water molecules here, and these are the silicon dioxide particles in the glass. So we have our water here, and this is the glass part on this side. Okay, so the water's here, and this is the glass. Okay, so if you're looking at these silicon dioxide substances, so these are just they're not the tetrahedral that you would expect. They're just they're double bonded like that. Just again a special type of molecule here. So yeah, you're gonna get the water coming in and oops, like that, and you're gonna end up H bonding this way as well. Okay, so the water will H bond with the glass, but the water will H bond with itself, and the silicon, so the glass is also H bonding to itself. So basically, so what's happening here is all the water is, holding hands together. Okay, they're holding hands together, but then they're also holding hands with the glass. So as you are, they're holding hands together here with the meniscus part, but then they're being pulled up by the glass because they're being silicon or hydrogen bonded to the glass as well. So that's why you get this meniscus effect here. Okay. Again, this is just a display of surface tension as well. So again, these intermolecular forces are allowing water to kind of counteract against gravity. So gravity should, have it nice and flat, okay, push the water down. But because of the H bonding and so forth that happens, water can creep up the side of the glass when it's like in a small tube like that. Okay. Now we're going to start looking at the phase changes of water and what's going on there. So again, you know that the water molecules will have hydrogen bonding between them. So like, again, this is oxygen, right? And this is hydrogen. Okay, they're bonded together, and they're going to attract the hydrogens, and the oxygens will create a hydrogen bond between them. Okay, so what's happening when there's a bunch of water molecules? So again, if we're looking at ice, that's the solid. Okay, and then we're getting to water, which is the liquid form here. So what's happening with respect to H bonding when you have different phases? So when you have ice, you're going to find that the water molecules are going to form hydrogen bonds. So these little red lines here are hydrogen bonds between the different water molecules here. Okay, so you create this shape here, and then you bond to some other ones this way and so forth. So it kind of creates this neat little hexagonal pattern here with the water in ice. Okay, and then what happens again, like, so maybe we warm up the temperature, and like maybe we start adding heat because we're or just the temperature of the room warms up, or the earth is warming up and so forth. So it's going to create these particles to start vibrating, right? So according to the particle theory, and when they start vibrating, these bonds will break, and then they'll kind of break apart out of the structure here, and then you'll still get a little bit of H bonding, but it'll be more where the water molecule is now separated and so forth, and it's not in a big structure like this. Okay, and then if we went to also to gas, then you would find that when the water molecule are even further apart with a lot more energy, then you get the gaseous form and so forth. Okay, so so that's we want to move into looking at the structure within solid liquids of water. Okay, so another interesting property that water has is whenever water freezes, it floats to the top. Okay, if you did the density experiments back in grade 9 elementary school, you would find that generally when you have a solid form of substance, it will sink to the bottom just because it'll be more dense and in the liquid and so forth. But we're finding that ice is kind of an exception here, where when it's solid, it becomes lighter and it floats up to the top. Okay, so we're going to look and see why that's happening as well. So again, hopefully you are now comfortable with the whole idea of H bonding and so forth, right? Because the water molecules have a partially negative and positive end, so they'll attract another water molecule like this and create these H bonds. So when you get to a solid form of water, they will actually freeze into this nice hexagonal, so 6 sides hexagonal shape like this. Okay, so it creates this lattice structure, and what happens is you have a lot of open space in between these hexagons, right? So to the next hexagon and so forth. So because you have a lot of these open spaces here, you have less density now compared to when you had water, which was back, like here's a good example of water. When it was liquid water, they're disorganized. They're not in these nice little hexagons and so forth, but they're closer together. Okay. Where when it's ice, it's like locked into this kind of organized structure, so there's a lot more space in between the water molecules. And so that's why when you when you freeze water, you just get, you get a glass of ice water, the ice floats to the top, and then the liquid water's at the bottom. The great thing about this property is that, like, for example, in a lake, you'll find that when it freezes over, you get the ice at the top, right? But it's still liquid underneath, and so the fish and the plants and so forth can still survive through the winter because yeah, like the ice is at the top, and then it's in a way that insulates the water as well, and so forth. So that's everything we covered in this lesson today. So again, we should be pros now at creating a three-dimensional diagram of water. Now we know it takes this bent shape, and you end up with a partially negative and positive end, so it's a polar molecule. And because of the fact that it's a polar molecule, it will lead to the different intermolecular forces. So it will have a London dispersion force, it'll have dipole-dipole, but a big one is that H bonding will contribute to a lot of its properties as well. So we looked at how, if you have the more intermolecular forces you have, the greater your boiling point, like it'll increase and so forth. And then if you have the H bonding, if you have fluorine, oxygen, or nitrogen in your structure, and you're bonding to a hydrogen, then you're going to have even a greater boiling point because of hydrogen bonding. Okay, and because that bond takes a lot more energy to break and so forth, and therefore to boil the structure. Okay. And then we also looked at another. So we looked at high surface tension to water. So again, you can pour, to over pour in a glass here, and then there's that little layer of water that doesn't spill over, and it's because of the hydrogen bonding. Okay, think of it as they're all holding hands, holding on, so that one water molecule on the side doesn't fall off. Okay, you also get this meniscus effect here, where water will creep up the sides of a glass if the glass is narrow enough. And again, it's overcoming gravity, because if it had gravity, it should be flat, but because it can H bond with the silicon dioxide in the glass, it can go up the sides as well. And so then we looked at the different the phase changes, right, from solid, liquid, gas. So and then ice, we know that it has a hexagonal shape because the hydrogen bonds kind of lock it into a nice organized structure, so that it leaves a lot of empty spaces here to make it less dense than liquid water, which is kind of more disorganized and closer together. Okay, so those are the properties of water that I wanted you to pick up today. So just kind of review those, and then answer some questions with your checkpoint.